Now come to the reactions of phenol. Following reactions are shown by phenols only. First type of reaction is electrophilic aromatic substitution. In phenols, the reaction that takes place on aromatic ring are electrophilic substitution reaction. The OH group attached to benzene ring activates it towards the electrophilic substitution. It also directs the incoming group to ortho and para positions in the ring as these positions become electron rich due to resonance effect caused by OH group. The resonance structures are shown under acidity of phenols. So let's draw the resonating structures of phenol. So this is the benzene ring in which alternate single and double bonds are there, and here it is bonded to OH. This is phenol, and we know oxygen has two set of lone pairs. As these lone pairs are in conjugation with the benzene ring, they participate in the resonance of benzene. One of the lone pair will shift between carbon and oxygen, and pi bond move to the next carbon. So here you will get the next resonating structure. In this resonating structure, these two bonds remain as it is. Here the carbon-oxygen bond become double. And now, as oxygen has donated lone pair to benzene, it will develop positive charge. And as the pi bond move to the next carbon, negative charge will be developed at this position. Now, in the second resonating structure, this negative charge will move between these two carbons and pi bond move to the next carbon. So here you will get the next resonating structure. In this resonating structure, these two bonds remain as it is, and oxygen already has the positive charge. New bond will be formed at this position and negative charge will be developed at para position. Now in the next resonating structure, negative charge will move between these two carbons and pi electron move to the next carbon. So here you will get the next resonating structure. In this resonating structure, these two bonds remain as it is. Oxygen already has the positive charge. New bond will be formed at this position and negative charge will develop at this position. So when you observe these resonating structures, you will see negative charge will develop at ortho position, here at para position, and here at ortho position. Due to plus R effect of OH group, electron density increases at ortho or at para position of benzene ring. That's why OH group is ortho or para directing, and it also activates the benzene ring towards electrophilic substitution reactions. Now let's read from the book. The common electrophilic aromatic substitution reactions taking place in phenol are as follows. First is nitration. With dilute nitric acid at low temperature 298 Kelvin, phenol yields a mixture of ortho and para nitrophenols. You have already learned nitration in benzene and in haloarenes. For nitration in benzene and in haloarenes, we have used nitrating mixture that consists of concentrated sulfuric acid and HNO3. But here in case of phenol, just dilute nitric acid is enough for the nitration. As OH group is ortho-para directing, you will get two derivatives, one ortho derivative and another para derivative. The ortho and para isomers can be separated by steam distillation. Ortho-nitrophenol is steam volatile due to intramolecular hydrogen bonding, while para-nitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecule. Now let's see the structure of ortho-nitrophenol and para-nitrophenol. In ortho-nitrophenol, hydrogen of OH group is closer to the oxygen of nitro group, so they can make hydrogen bond with each other. In case of ortho-nitrophenol, hydrogen bonding takes place within the molecule. That's why it is called intramolecular hydrogen bonding. This hydrogen bonding doesn't affect the boiling point of the molecule. While in case of para-nitrophenol, hydrogen of OH is far away from the oxygen of nitro group of the same molecule. So it can make hydrogen bond with the oxygen of the another molecule. This type of hydrogen bonding is called intermolecular hydrogen bonding, as it is formed between two molecules. Such hydrogen bonding decreases the boiling point. So that's why para-nitrophenol is less volatile due to intermolecular hydrogen bonding. Now let's read from the book. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol. The product is commonly known as picric acid. The yield of reaction product is poor. So when you increase the concentration of nitric acid, so if you take concentrated nitric acid instead of dilute nitric acid, nitration will take place at all the positions, both ortho and para position, and it results in the formation of 2,4,6-trinitrophenol. This derivative of phenol is also called as picric acid. So why does the phenol derivative is named as an acid? Now let's try to understand it. We know acid is a molecule which donates H plus ion. Here in case of trinitrophenol, this is oxygen and it is bonded to hydrogen. Here at 2, 4 and 6 position, nitro group is there. So this is 2,4,6-trinitrophenol. And we know nitro group is electron withdrawing group. It withdraws electron density from oxygen. So as it withdraws electron density from oxygen by minus M effect. Ultimately oxygen will withdraw electron density from hydrogen and it weakens the bond between oxygen and hydrogen. That's why it facilitates the removal of hydrogen in the form of H plus ion. So due to presence of 3 electron withdrawing group at ortho and para position, this derivative of phenol easily donates the H plus ion. That's why it is also named as picric acid. Nowadays picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it into phenol 2,4-disulfonic acid, and then with the concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the equations for the reaction involved? So let's try to write the reaction involved here. So this is the phenol, and we already discussed that phenol OH group attached to benzene ring activates the benzene ring. So when it is treated with the concentrated nitric acid, this reaction produces lots of heat and the yield of the product is also very poor. That's why alternate method to produce picric acid is used. In this alternate method, phenol is first treated with concentrated sulfuric acid. So here when it is treated with concentrated sulfuric acid, it results in the formation of 2,4-disulfonic acid. So here this is the benzene ring and here OH group is bonded. At 4th position, sulfonation takes place. So here you will get SO3H and here also you will get SO3H. This SO3H group is electron withdrawing group. This is electron withdrawing group. It withdraws the electron density from ortho and para positions. So as it withdraws electron density by minus M effect, it deactivates the benzene ring. As it deactivates the benzene ring, now the nitration will become less vigorous, means less amount of heat will be released during the nitration. As it deactivates the benzene ring, nitration cannot take place with the dilute nitric acid. Now you will require concentrated nitric acid for the nitration. Nitro group also replaces the sulfonic group. So here you will get picric acid as a result of nitration. So nitro group will get attached to 2, 4, 6 positions with respect to OH group. So that's how picric acid can be prepared. Now come to the next reaction, halogenation. On treating phenol with bromine, different reaction products are formed under different experimental conditions. When reaction is carried out in the solvent of low polarity, such as CHCl3 or CS2, and at low temperature, monobromophenols are formed. So here when bromination takes place with a non-polar solvent like carbon disulfide, bromination takes place either at ortho or para position. Here para derivative is the major product of the reaction, while the ortho derivative is the minor product of the reaction. In ortho derivative, there is steric hindrance between OH group and Br. So that's why due to steric hindrance, ortho derivative is a minor product, while in case of para derivative, there is no steric hindrance between OH and Br. So that's why it is the major product of the reaction. The usual halogenation of benzene takes place in the presence of Lewis acid such as FeBr3, which polarizes the halogen molecule. In case of phenol, the polarization of bromine molecule takes place even in absence of Lewis acid. It is due to the highly activating effect of OH group attached to the benzene ring, which helps to produce electrophile. In case of halogenation of benzene or the halogenation of haloarenes, we require Lewis acid, which help to produce the electrophile. But here in case of phenol, it doesn't require any Lewis acid. Phenol itself polarizes the bromine molecule to produce electrophile. Now come to the next condition. When phenol is treated with bromine water, 2,4,6-tribromophenol is formed as a white precipitate. In case of bromine water, bromine is dissolved in water and water is a polar solvent. So when polar solvent is used with the bromine, bromination takes place at all the positions and it results in the formation of 2,4,6-tribromophenol, which is formed as a white precipitate. This reaction can be used to distinguish phenol from the other alcohols. Now let's try to solve example 7.5. Write the structures of the major product expected from the following reaction. Mononitration of 3-methylphenol. Now let's write the reaction. First of all, draw the structure of 3-methylphenol. So this is benzene ring and here OH group is bonded. This is phenol. At third position, methyl group is bonded. So this is the third position where CH3 group is bonded. When it undergo mononitration, so here it will require dilute HNO3. And you know OH group is activating group and this is ortho para directing group. CH3 is also an activating group and this is also ortho para directing group. So nitration will take place either at ortho and para position with respect to these groups. And as OH group is the strongly activating group, it will take the responsibility to direct the coming electrophile. Now let's draw the product of this reaction. So this is 3-methylphenol. There are two ortho positions with respect to OH. The nitro group may get attached to at this position or it may get attached to the another ortho position. So let's draw the structure. So this is OH. This nitro may get attached to this ortho position with respect to OH and there will be another product which is a para derivative. So here this is 3-methylphenol. Now nitro group may get attached to the para position with respect to OH group. When you observe these products, in the first product there is too much steric crowding between nitro group, OH group and CH3 group. So that's why this product will be less stable because of the steric crowding. So it will form in the minor proportion. But when you compare the other products, there is enough space between the groups attached to the benzene ring. So these two products will be formed as a major product. Now come to the second question. Dinitration of 3-methylphenol. Now let's draw the structure of 3-methylphenol. So this is, again I am going to draw 3-methylphenol. This is OH and here methyl group is bonded to third position. Again you will require just dilute nitric acid because both the groups are activating groups. This time we have to do dinitration. So it will undergo dinitration. This is OH group and this is CH3 group. As we have already discussed, this position is sterically hindered position. So we are not going to attach nitro group at this position, but we can attach nitro group at ortho position as well as at para position. So nitro group will get attached to para with respect to OH and ortho with respect to OH. So this will be the product of dinitration of 3-methylphenol. Now come to the third question. Mononitration of phenyl methanoate. First of all, draw the structure of phenyl methanoate. So let's revise the naming of ester. This is R, O, C double bond O, R. So this part of the molecule is named as alkyl and the rest of the part will named as alkanoate. So here the name is given phenyl methanoate. So this is phenyl part and this is methanoate. The name is methanoate, means it contains just one carbon. Now let's draw the structure of phenyl methanoate. Phenyl means benzene having one free valency. It's called phenyl. So this is the benzene ring and here it is the free valency. So now it becomes phenyl. Phenyl is bonded to O and O is bonded to C double bond O. As it contains just one carbon, the R group will be H. So now this is the structure of phenyl methanoate. This is phenyl methanoate. I have confirmed this structure from the reference book. Here the structure which is given, this is wrong. It should not contain CH3 group here. It should bond it to hydrogen. Now when it undergo mononitration. Now let's identify the nature of the group attached to the benzene ring. Here electronegative element O is directly bonded to benzene ring. So that's why the nature of this group is the activating nature. So it will donate electron density to benzene ring as oxygen has lone pairs of electron. So it also activates the benzene ring. So for the nitration, it only requires dilute HNO3. As it activates the benzene ring, it is a ortho-para directing group. So nitration will take place at either ortho or at para position. As the group attached to benzene ring is quite bulky, so ortho derivative will be minor product and here you will get the major product as para derivative. So this will be the major or the single product of this reaction. Now come to the next reaction. Next reaction is Kolbe's reaction. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. Hence it undergoes electrophilic substitution with carbon dioxide, a weak electrophile. Ortho-hydroxybenzoic acid is formed as a major product of this reaction. Now let's observe the reaction given here. Here this is phenol and we know phenol is acidic in nature. So when it reacts with base NaOH, it undergoes neutralization reaction and salt is formed. This salt is sodium phenoxide. Here sodium is positively charged and oxygen carries negative charge. So this phenoxide ion is more reactive than phenol. So that's why it may undergo electrophilic substitution reaction with weak electrophile like carbon dioxide. As it is an activating group, it directs the coming electrophile at ortho or at para position. When it directs the coming electrophile at ortho position, carboxylic group will get attached at ortho position. Common name of this molecule is salicylic acid. IUPAC name of this molecule is 2-hydroxybenzoic acid. Carboxylic acid is the main functional group. So here hydroxy group will be the secondary functional group. For hydroxy you have to use the prefix hydroxy and the name of this molecule will be 2-hydroxybenzoic acid. Now come to the next reaction. Next reaction is Reimer-Tiemann reaction. On treating phenol with chloroform in presence of sodium hydroxide, CHO group is introduced at ortho position of benzene ring. This reaction is known as Reimer-Tiemann reaction. The intermediate substituted benzyl chloride is hydrolyzed in the presence of alkali to produce salicyl aldehyde. Now let's observe the reaction. In this reaction, when phenol is treated with chloroform and with aqueous NaOH. With aqueous NaOH, phenol undergo neutralization reaction and result in the formation of sodium phenoxide ion. As this phenoxide ion activates the benzene ring towards electrophilic substitution reaction and directs the coming electrophile either at ortho or para position. CHCl2 group will get attached to ortho position. This is the intermediate of the reaction. It hydrolyzes in presence of alkali to produce salicyl aldehyde. So here you will get CHO group at the ortho position by the hydrolysis of CHCl2. When it is further treated with acidic solution, it results in the formation of salicyl aldehyde. Here aldehyde group is bonded at ortho position to phenol, and the common name of this molecule is salicyl aldehyde. Now come to the next reaction. The reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. So when phenol is treated with zinc dust, it undergo reduction and result in the formation of benzene. Now come to the next reaction, oxidation. The oxidation of phenol with chromic acid produces conjugated diketone known as benzoquinone. In the presence of air, phenols are slowly oxidized to dark colored mixture containing quinones. So when phenol treated with sodium dichromate in presence of sulfuric acid, it results in the formation of conjugated diketone. This is the ketone functional group, and these ketones are in conjugation, and the name of this molecule is benzoquinone. It is a dark colored compound. Now you can try to solve these questions, and if you have any doubt, you can post it in the comment box.